Hey guys, in this video, we're gonna be looking at trigonometric functions and the coordinates in the Cartesian plane. So before we begin, let's think about a circle on the Cartesian plane. So with this circle, we're just gonna generalize it. Let's say this circle has a radius of r, and it meets the circle at some point x comma y. Now, with this, we can actually see that there's an angle theta, using this as our initial side. So there's an angle theta, and we can apply our trig functions to this circle. And what we're going to be doing is, if I look at this and say this coordinate's x comma y, well, that's actually saying that we went x to the right and some y value vertically. So we took this and we're now seeing a right triangle out of it, and with this right triangle we're able to write all of our sine, cosine, tangent ratios. So looking at this, our sine ratio, sine of theta, would be opposite over the hypotenuse, so opposite y, hypotenuse r, so y divided by r. And then our cosine would be adjacent over hypotenuse, so x over r. And then we can write our tangent ratio to be opposite over adjacent, or y over x. So this for any circle on the Cartesian plane. Really, we're not going to be seeing a circle, we're just going to be seeing a coordinate. For any coordinate on the Cartesian plane, we are able to write the trig ratio for that coordinate, knowing that the radius will be the direct distance to the coordinate, and we'll get to that when we see more examples. So this is just for any circle. But what if we have a circle of radius 1? So we call this, if a circle of radius 1, we call this a unit circle. So how do our trig ratios change if our radius is 1? Well, our radius is 1, just looking at these, wherever we see a radius, it's just 1. So what's interesting, and we're going to be looking at this more later on, is that we could then say that for theta, sine of theta is essentially just y. And cosine of theta is essentially just x. And that might not seem much to you right now, but what we can say then is, with a unit circle, the x coordinates are going to be cosine of theta, the y coordinates are going to be sine of theta. So I could rewrite x comma y, we can simply view it as cosine of theta comma sine of theta. And we're going to touch more on this later on. So let's actually look at an example. So the main part of this video, what we're focusing on, is the trigonometric ratios when we have an angle meeting at a point. So what I mean by that, so we need to say, let's look at theta. Let's let it be an acute angle whose terminal side contains, for this first example, let's let it contain 5, 3. Now that's going to be the typical directions for most of these problems. Let theta be an acute angle whose terminal side contains 5, 3. So we know 5, 3 is in the first quadrant, so 5, 3, just roughly estimating where that is. And we're saying that we have an acute angle whose terminal side, we know what that means, terminal side contains that point. So theta is this value here. All right, so we want to find let's find the sine of theta. So I can find the cosine theta, tangent of theta, but let's just find the sine of theta for this first example. So what we do here is we create something called a reference triangle. So I'm going to write this up here. A reference triangle. So what a reference triangle is, it's a right triangle drawn to the x-axis. So it's just to refer to when writing our ratio. So out here, I would say, so here's our 0.5, 3, so our reference triangle would be right here. And with this triangle, we know, according to this coordinate, that we have 3 being the y value, and 5 being the x value. And we have a right triangle, so I can find sine of theta, but we don't know what our hypotenuse or the radius is. We don't know what that value is, but we can find it. So we know r squared will equal 3 squared plus 5 squared. So doing our computation here, we would find that r equals the square root of 34. And yes, we're leaving it just as the square root of 34. All right, so we have the radius, we have the hypotenuse, so sine of theta would be, therefore, opposite 3 over the square root of 34. And yes, we could simplify it, but for right now, we're actually okay with just writing it like that. And we could easily write it, if you're curious, it would end up being 3 square root 34 over 34. All right? So that might not seem much to you, but what's going to happen is, well, we know there are coordinates all throughout this Cartesian plane in the different quadrants, and we're going to see how the trig ratios change. So let's say we have, with that being said, let's say we have, a theta being an acute angle whose terminal side, let's let it contain the coordinate -3, 6. So -3, -6. So we're right here in the third quadrant. All right, so we have an angle whose terminal side contains that point. So our initial side and then our terminal side contains that point. So we want to write all 6 trig ratios. But that's our goal here. Based off of this, with our theta, we want to write all 6 trig ratios. To do that, we first draw our reference triangle, which from our point, we drop a line to the x-axis, and it is always to the x-axis. Always to the x-axis. So we have our right triangle here. And then from there, theta, with that being said, theta is always touching the x-axis. So I would never see theta as on this side. So theta is on the touching the x-axis. So we have this. What's interesting is that this length, our components, we have -3 and -6. And you say, well, we have lengths that are negative. Well, in the Cartesian plane, those negatives simply refer to which quadrant we're in. So we have -3 and -6, and that's okay. So I want to find all 6 trig ratios. Well, I need the radius first. So our radius would be r squared equals -3 squared plus -6 squared. Doing our computation, we get r to be the square root of 45. And I'm going to make a note right now. Because of how we find the radius r, the radius will always be positive. So where our x and y might change depending on the quadrant it's located in, the radius will always be positive. That's actually very important to know. So we have our radius, the square root of 45. We're now able to write our trig ratios. So, going through these rather quickly. So sine of theta would be -6 over the square root of 45. All right. Cosine of theta would be -3 over the square root of 45. And tangent of theta would be -6 over -3. And yeah, let's go ahead and just simplify that down to 2. We can, rather quickly. So let's write our reciprocal ratios. So cosecant would be square root of 45 over -6. Secant would be square root of 45 over -3. And cotangent would be 1 over 2. So you're noticing something new. We have trig ratios that are negative, and that's actually one of the new additions to this topic, is that because our angle measures are no longer confined to 0 to 90 degrees, we are going to be having ratios that are negative, and the negative is simply due to the location on the Cartesian plane. So next example. So we're just going to practice this some more. So in our next example, let's say we're given theta is in quadrant 4. Okay, so theta is in quadrant 4, and sine of theta is -3 over 5. Then find cosine of theta. All right, so a couple of things here, so it's kind of good to know. So we're in quadrant 4. So we're in quadrant 4, that's, this lovely position. And we don't know exactly what our point is, and that's okay. So our theta, we want to draw our reference triangle. So using theta to be here, because theta is always against the x-axis. Yes, this theta is comparable to the theta on the outside. We know that they're the same terminal angle, to the coterminal angles. So -3 over 5. The -3 should make sense because this coordinate is below the x-axis. So -3, and hypotenuse 5, so our radius is 5. So for cosine, we need this adjacent. Well, we know how to find it. So we'll say 5 squared equals, I'll use this as x squared since that's essentially what this is, x squared plus -3 squared. Understand this coordinate, we know that our y component is -3, but we do not know the x component, and that's what's needed for the cosine. In solving this Pythagorean theorem, we would find that we get x to be +4. You get square root of 16, but it ends up being +4 when solving it. Okay, so we have our x components 4, so cosine of theta then will be 4 over 5. So where sine was negative, our cosine ratio is positive. Let's try another. And let's say, given theta, let's have theta to be between pi over 2 and pi, and sine of theta to be 8 over 17. Find all 6 trig functions, ratios. All right, so pi over 2 to pi, so pi over 2 is in the 90 position, pi is in the 180 position. So we're in this region, and we have sine of theta. Sine of theta is 8 over 17. So we make our reference triangle, drop our line to the x-axis. Our theta is touching the x-axis. Sine of theta would be 8 over 17. So we need all 6 trig ratios, so I would need to find our x value. So Pythagorean theorem, Okay. And solving this, you get x to be 15, but we have to recognize with which quadrant we're in, this essentially will be a negative 15 because of the quadrant we are in. So x is negative 15 again. I'll say that again, negative 15. Now we can write our ratios. So let's say we know what sine of theta is. That was given. Cosine of theta, negative 15 over 17. Tangent, 8 over negative 15. And cosecant, just a matter of all the reciprocals, 17 over 8. 17 over negative 15. And negative 15 over 8. So we've gone through four examples here, and you're noticing that the sine and cosine ratios are negative, and they're not always negative, they're not always positive. It's just within certain locations on the Cartesian plane, their signs change. So we're going to close this video with summarizing when will sine of theta be positive, when will cosine of theta be positive, and with that we can know when they're negative. See, we're just summarizing, so we're going to title this last section to summarize positive, negative quadrants. So signs of trig functions. All right, so we have quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So we know, just from our understanding of the Cartesian plane, that in quadrant 1, our x and y components are going to be positive. Quadrant 2, x components negative, y components positive. Quadrant 3, they are both negative. In quadrant 4, we have positive x component, negative y component. And also at the very beginning, we also know that sine and cosine relate to an x and y value. So if you remember, if you need to rewind, do so. But if you remember, cosine is the x component, sine was the y component. Again, yes, that was a unit circle, but it's comparable to any circle as well. So what we see here is cosine in the first quadrant, cosine will be positive always, sine will be positive always. And then second quadrant, cosine is going to be negative, sine is going to be positive, and quadrant 3, they're always both going to be negative. Quadrant 4, cosine's positive, sine's negative. Now this is when theta, when the terminal side lands within the quadrant. So if I have a terminal side within quadrant 4, I know cosine's going to be positive and sine's going to be negative. A way to remember this is, what's actually, before I talk about that, tangents. We see sine and cosine. Tangent, if both sine and cosine are positive, tangent's going to be positive. If we have cosine to be negative, sine to be positive, tangent will be negative. And when they're both negative, tangent will be positive. And we have positive and negative, tangent will be negative. Okay, so looking at this, a way to remember that what I'm about to show you is a way to remember which quadrant, which trig ratios are positive in the quadrants. Okay, so I'm gonna write this down. All students take calculus, or you'll eventually just know it as ASTC. Okay, so what this is saying, in the first quadrant, all trig ratios are positive. In the second quadrant, only sine is positive, and also with that cosecant, it's reciprocal. In the third quadrant, only tangent is positive, and with that cotangent. And then in the fourth quadrant, only cosine is positive. So a good way to know the signs of our ratios. So let's use this. Use this and answer some questions. What quadrants can theta lie if, so first one, if sine of theta is positive and cosine of theta is negative? So sine of theta is positive in quadrants 1 and 2, okay? Cosine of theta is negative in quadrants 2 and 3. So where must theta be for both of these to happen? Quadrant 2. So I did that. I looked at sine where it's positive, cosine where it's negative, and the overlap is where our theta must be. Let's try another. So let's say we have sine of theta and tangent of theta have the same sign. All right. So sine and tangent have the same sign. Okay. So sine's positive, tangent's positive in the first quadrant. Let's see if there are any other. Tangent's negative, sine's positive, no. Tangent's positive, sine's negative, no. Tangent's negative, sine's negative. All right, so we're seeing tangent's negative, sine's negative, quadrant 4. And tangent's positive, sine's positive in quadrant 1. So I'm going to leave you with 2 more here. Actually, just one more to leave off. So what about cotangent of theta and secant of theta having opposite signs? So take a moment to think about that. What you should find is that these have opposite signs. So cotangent, we can compare it to where tangent is, look at the signs of tangent. And same with secant, we can compare that to cosine. You should find that they have opposite signs in quadrants 3 and 4. All right, so we've talked about trig functions in the Cartesian plane, how we can have positive, negative trig functions, and we're ending here with knowing where the trig functions are going to be positive and extending that where they can be negative as well. All right, so I wish you the best of luck in the practice, and I'll see you in the next video.